Hello friends, I am Kanchan Vaidya from Bureau by Savan College of Engineering and Research. I am from Electronics and Telecommunication Department. Now we are here discussing about the introduction of network analyzer. It is a study practical. So the title of the experiment is Study of the Network Analyzer and carry out its measurement of the S parameters. So the objective of this practical is to introduce the network analyzer and its measurements. As it is a study practical, so here I am going to explain you the introduction of the network analyzer, its history, and how the S parameters are being calculated on the network analyzer. So after going through this video, you will understand the parameters measurement, its history part, and the complete introduction of the vector network analyzer. So let's start with the introduction of the network analyzer measurements. Actually, before the network analyzer, determining the reflection coefficient of the circuit, which is required you to manually calculate the phase of the reflection coefficient, one frequency at a time on piece of paper. So this manual process required you to first find the maxima and minima of the standing voltage wave in a slotted line and repeat this process for all the frequencies. So it is safe to say that if the vector network analyzer had not been created, the high frequency community would look very difficult today. So today, the VNA characteristics or this characterizes the high frequency passive and active devices in their linear mode of operation by measuring their network parameters called the S parameters as a function of frequency. So over the time, VNAs have been extended in hardware and in capability to also measure the noise parameters, nonlinear characteristics, including compression, intermodulation, and hot ST2, that is S22 measurements. So as a result of it, VNA evolved into an instrument enabling multiple measurements with a single connection. So now here you can see a diagram on the screen. So it is in its simplest form, a network analyzer is an instrument which is used to measure the impedance. So at lower frequencies, you can measure impedance with relatively simple tools, that is including a sine wave generator, a voltmeter, a current meter, and a calculator. So using these tools, you can measure a ratio between voltage and current, and you can calculate the resulting impedance as you can see here in the diagram. At the RF and microwave frequencies, the measurements of voltage and current become more complex. So, the VNA uses a more complex design to measure the incident and reflected waves. So, in many waves, the VNA it marries the principle of basic impedance measurement with hardware and the appropriate for the microwave frequencies. So, when using the VNA to measure the impedance or the reflector factor, a sine generator stimulates a device under test. So, in addition to it, two receivers take a place in the combination of a voltmeter and the current meter. And these receivers, with the help of signal separator hardware, and characterizes the response of the device by measuring the phase and the amplitude of signals that are both incident and reflected from the DUT, that is device under test. So finally, a calibration capabilities are required to eliminate the systematic errors and to compute the appropriate ratios, which is necessary to produce S11, which is one of the part of S parameters. So the architecture of this simplified VNA that you can see here in this figure 1.2. So to measure the devices with more ports, the architecture needs to be extended. So the modern network analyzer covers a wide range of frequencies from low hertz to tens of terahertz. Applications of the network analyzers are seen the primary use of VNA is to use the S parameters of a myriad of the passive components that includes cables, filters, switches, duplexers, triplexers, couplers, bridges. transformers, power splitters, combiners, circulators, isolators, attenuator, antennas, and many more. So, in addition to VNA, one can characterize the active devices such as transistors, amplifiers using S parameters. So, as long as they are operating in the linear mode of operation, high frequency divide or these devices can have one or more ports. So the RF and microwave S parameters provide complete insight into the linear behavior of the RF and microwave components, and they are independent of the characteristics of VNA itself. So though the VNA calibration and impairments of the instruments are completely removed from the measurement, the S parameters are an extremely accurate representation of the linear behavior of the component which is under test. So describing how it behaves and how it interacts with the other devices when it is cascaded. So for that reason, you can use the S parameters in a wide range of application, which is ranging from a simple metric to characterize the circuit performance to a basic behavior model in electronic design automation tools. So in a latter case, like S parameters enable the stimulation of the complete RF circuit chains. S parameters are very useful because they are an integral part of different theories, such as filter, transmission line, and amplifier design theories. Also, the S parameters are essential in performing proper noise parameter measurement. While, while being an engineer, we are increasingly facing nonlinear problems. So, they mainly design for linear modes of operation and for the engineering tools is still based on the linear theories. So other use over these VNAs have been found their way into applications beside the pure S parameter measurement capabilities. So modern VNAs are being used for the characterization of the dielectric properties of materials or even the human brain. So now we'll see the history of the network analyzer. See in 1950s, in the early part of the 1950s, the Rohit and the Squared had achieved a breakthrough in the network analysis with the product called the ZG diaphragm. So until then, the network analysis has been limited to the manual measurements of the standing waves in a slotted line. So that ZG that is covered a frequency range of 30 megahertz to 300 megahertz. So the 2.6, 2.4 gigahertz. So this measurement became the first complex network analyzer on the market that would directly measure the phase of S parameters and display the S parameters on the Smith chart. So the ZG was used to measure the radios, TV antennas and some telecommunication cables. So between these 1950s and the early 1960s, three other companies that introduces a form of network analyzer based on the homodyne principle. In 1965, the Wilter has introduced 310 impedance meter. So during that time, other companies such as Headline Corporation and the Ratley Corporation, they have created some of the world's first network analyzer. In the 1990s, the growth in the high frequency systems such as cellular telephones and cable television created increasing demand for instrumentation that was capable of characterizing the RF and microwave circuits. So, as the demand for VNAs increased, it is began to enjoy the broader range of price points and the performance capabilities for VNAs. So, as a result of it, the market saw various low-end VNAs being commercialized and deployed into the test and manufacturing environments, while the high-end VNAs continued to target research and development. So, meanwhile, the scalar network analyzer had been replaced by the VNA in many applications due to VNA benefits such as reduced cost and technical advantages. One key innovation in the network analysis technology in the early 2000s was the evolution of VNA towards measuring devices in their non-linear range of operations. So, as the RF and microwave components have been pushed to their limits, an increasing number of engineers are required to characterize the non-linear behavior of the devices which are under test. So, the need for measurement beyond S parameters, which only describe the linear behavior, that has imposed a new requirement on the VNAs to measure the additional device characteristics, and it requires the presence of the combined source and receivers. So, as a result of it, a wide range of vendors such as Agilent Technologies have begun to develop a non-linear network analysis technology. And given the challenge of the modern network analysis, that the complexity of the network analysis technology has evicted the role of software in the VNA system. So, as a result of it, PC based form factors are increasingly popular choice for VNA. And then in 2012, National Instrument introduces the first PXI based VNA, that is the NI PXIE 5630, which was followed 1 year later by the NI PXIE 5632 with full S parameter measurement capability, which you can see here in this diagram. Now we will see how the wave quantity measurement takes place. So the S parameter describes the complete linear behavior of the high frequency device or a circuit in a linear mode of operation. The main function of the vector network analyzer is to provide the S parameters as a function of frequency. So although the modern VNAs return S parameters with a push of button, as the S parameter is not a quantity that can be measured directly, instead the S parameters are the result of a solving a set of equations after measuring ratios of wave quantities while exciting the device at its various ports. So measuring the wave quantities, the properly understand S parameters, you must first understand the theory of the process and measuring the wave quantities. So consider an example. A load connected to a sine wave generator through a piece of cable, as you are here you can see in a figure number 2.1. The sine wave generator has a certain source impedance and the electrical power travels across the wire from the source to the load as the combination of electric and magnetic field. The propagation speed that depends on the dielectric properties of the medium, and it is a fraction of the speed of light. The wavelength is defined as the function of propagation speed, and the sine wave generator, the frequency can be here, we'll get that formula lambda is equals to Vp upon frequency 0, that is the generator frequency f0. So when the frequency is low, the wavelength is large and the length of the cable is negligible as compared to the size of the wavelength. So as a result of it, the measured voltage and current are independent of the location on the cable. So this situation is here shown in figure number 1, and the circuit is referred to be being a lumped element circuit or the lumped circuit. Now when the frequency of the source increases, then the wavelength is reduced. Thus the frequency increases, the wavelength eventually becomes similar in size or even smaller than the length of the cable. Now in this scenario where the wavelength of the signal is similar or smaller in size to the length of the cable, the measured voltage and current will depend on the position as here shown in the figure number 2.2. Thus the measuring of the voltage with the voltage probe is invalid because the result will be dependent on the probe's position. So see, in this scenario when the circuit must be treated as a distributed element, the circuit rather than the lumped circuit. So as the analysis of the distributed circuit, it is more complex and it involves the use of transmission line theory. So using the transmission line theory, you can just think of the electrical power traveling along the starting from the source and while traveling on the line. So certain voltage, that is E field, and current H field, the relation is imposed by the electrical properties of the line. In fact, I can say a cable itself will behave such that it is characterized by an inherent impedance that does not change as long as the properties of the line or cable do not change. So this impedance is called as the characteristic impedance, which we always denote by Z0. So as the electrical power hits the termination, that is load, the voltage to current relationship is now imposed by the impedance of the load. Under the condition where the load impedance is equal to the characteristics impedance, the power is fully absorbed. So to keep the reasoning simple, real impedances are assumed here. So if the load impedance is different from the characteristics impedance, the ratio of the voltage and current will change at the point where the transmission medium occurs. So as a result, the load will not absorb all the power and resulting in the portion of the power traveling back towards the source. So giving this characteristics, we can refer to the system as having both incident and reflected wave. The ability to separate the incident and reflected waves is a critical element of the network analysis, not only because it identifies how much power is absorbed by the load, but also because it reveals the information about its impedance. So, as a result of it, one of the most important function of VNA is to separate these incident and reflected waves by means of either by the coupler or by the bridges in order to measure each of these waves independently. So, thus, while measuring from simple volt and current meters, we are able to determine the impedances and transfer function of the circuits at lower frequencies. So, measuring similar characteristics at higher frequencies, it requires the measurement of incident and reflected waves. In fact, when VNA is able to measure the amplitude and the phase difference between the individual waves using one of the wave as a reference, the modern VNAs are even able to measure these quantities in an absolute way instead of the relative way. So, figure 1.2, it clearly shows the signal separation hardware which separates the incident and the reflected waves using the directional coupler. Now we'll see the introduction of the S parameters. Now determination of the scattering parameters or the S parameters, it is the basic measurement capability of the VNA. The S parameters describe the magnitude and phase relationship between the incident and the reflected waves, and they are numbered according to where the wave originates from where it propagating to. So the term scattering parameters comes from the scattering matrix which is described in 1965 IEEE article, which is entitled by a power waves and the scattering matrix. Today, scattering matrix results such as S21, for example, they are displaying on the VNA display screen with a simple push button. So moreover, the instrument is able to apply the appropriate calibration techniques to remove a wide range of inherent impairments of the instrument itself. And in order to better understand these parameters in an intuitive way, it is useful to first consider in an example. See, in order to better understand the S parameters, it is useful to first consider an example from the field of optics. So the behavior of light through varying transmission medium. Suppose a light beam is shining on the lens. Here you can see in this diagram, see a light which is varying through the transmission mediums. So a light beam is shining on a lens. So in this example, we have shown some light will pass through the lens, which is undergoing the influence of the lens. So however, some light will also be reflected back by the lens towards the direction of light source. So in addition, it is also useful to investigate what happens if the light passes through the lens and if there is no obstacle between the lens. So the light will continue to travel forever. If an obstacle exists, however, the part of the transmitted beam is reflected back towards the lens. So this light will be partially reflected back towards the obstacle and it will be partially transmitted through the lens. Thus, the reflection from the obstacle is added to the initial reflection from the light source. As a result, the reflected wave before the lens consists of two parts: the original beam reflected from the lens and the part of the reflection from the obstacle. Similarly, the transmitted wave consists of the original beam transmitted through the lens and partially the reflected beam from the obstacle, as here you can see in the figure number 2.3. See here the lens and the light analogy that translates easily to the understanding of the way the waves travel through the electrical circuit. So here in this diagram, both this B1 and the B2 wave can be described as a combination of both A1 wave and the A2 wave. These relationship can be formally represented as a S parameters equation for a two-port device in the following equations. So here you can see B1 is equals to S11A1 plus S12A2 and B2 is equals to S21A1 plus S22A2. So these equations are for two-port devices. So it is important to realize from the equation 2.2 that when the wave leaving a device under test is a linear combination of the waves entering the device under test. So as a result of it, while terminating the device, in the characteristics impedance, it allows the extraction of the individual S parameters. For example, when we have the characteristics impedance, it is equal to 50 ohms. And if the 50 ohms termination is present at port 2, so A2 is reduced to 0, resulting in the equation of S11 and S21. This principle can be applied in the reverse direction as well. So by setting A1 to 0, we can obtain the equation for S22 and S21 as shown here. So here you can see in equation number 2.3, S22 and for S12, the equations are obtained. Now here we have to note that a common notation is to use for the subscripts M and N for the general S parameters, where M is the receiver port and N is the source port. For example, S12 is the transmission coefficient for the wave sourced at port 2 and received at port 1. So keeping in mind that these ratios are complex valued and the S parameters will carry both the magnitude and phase component as the function of frequency. So finally these equations can be converted into the matrix ports and we'll get it in the form of here shown in the equation number 2.4. So this is the theory part where we can determine the S parameters using VNA. It is a straightforward process. In practice, however, it is impossible to terminate the ports opposite to the driving port exactly in the characteristics impedance, which results in the presence of the reflected wave all the times. So this is how we have seen the how a vector network analyzer is useful for the calculations of S parameters. Thank you.